Welcome to the second part of the factor theorem. Today we're going to take a look at more complex applications of this mathematical theorem. What if the leading coefficient of a polynomial is different than 1? So we're not looking at an x minus b factor. How do we use the factor theorem to find the factors of this polynomial? In our case, we have a polynomial p of x divided by the polynomial 2x minus 1. Let's first start by doing the long division exercise and find the quotient of this particular polynomial. So 2x cubed minus 5x squared minus 4x plus 3 divided by 2x minus 1. How many times does 2x go into 2x cubed? X squared times multiplication step followed by subtraction step. Please remember to lower all the remaining terms from the original polynomials. How many times does 2x go into negative 4x squared? Well, negative 2x times. Multiplication step will be followed again by a subtraction step. And we have a remainder of negative 6x plus 3. And lastly, minus 3. And multiplication followed by subtraction, we show that we will actually have a remainder of 0. Well, what does that mean, that we have a remainder of 0? It means that 2x minus 1 is a factor of the polynomial p of x. Polynomial p of x can be written as a multiplication of two factors, 2x minus 1 and the newfound quotient based on the long division exercise, which was x squared minus 2x minus 3. So 2x minus 1 is our original factor, x squared minus 2x minus 3 is our quotient. What does it mean to have a factor of 2x minus 1? Well, if we look at that particular bracket, it means that if we plug in 1 over 2 in the polynomial, we get a value of 0. Now, please remember to factor the quotient as well, especially it's a simple quadratic polynomial. And that leads us to conclude that also the polynomial at 3 and the polynomial at negative 1 will also have remainders of 0, since x minus 3 and x plus 1 are factors. Well, let's think about formalizing that rational zero theorem. Yesterday we looked at the integral zero theorem. Today we're going to expand that into the rational zero theorem. It means that for polynomials p of x with integer coefficients, in order for a binomial ax minus b to be a factor, then the polynomial at b over a equals 0, where a is a factor of the leading coefficient of that polynomial, and b is a factor of the constant. So a factor of the leading coefficient and b is a factor of the constant. So let's put this theorem in practice with our first example. We have our polynomial p of x, and let's identify what is b and what is a. Well, b we said is represents the constant, and a is the leading coefficient. So what are some of possible factors of the constants? We have positive and negative 1, positive and negative 5, and possible factors of the leading coefficient are positive and negative 1 and positive and negative 3. Let's look at possible b over a values. Well, all you have to do is take the different possibilities: 1 over 1, 1 over 3, 5 over 1, and 5 over 3. Of course, each one of these values could be positive or negative, generating a variety of possibilities. Let's apply the factor theorem and check each one of these values to see if it generates remainders of 0. The polynomial at 1 we notice equals 0, and we actually got lucky finding a factor of this polynomial that quickly, which means that x minus 1 is a factor of p of x. As soon as you find a factor, I want you to go back to your long division experience and find the quotient of the division between p of x and the newfound factor x minus 1. So we're going to divide our polynomial 3x cubed minus 19x squared plus 21x minus 5 by x minus 1. take a couple of minutes and do the long division on your own, because this way you're gonna keep practicing this particular skill and you're gonna get that much faster and that much better at it. However, in the interest of time, I can tell you that once we perform that division, the result of the division, or the quotient, is the polynomial 3x squared minus 16x plus 5, which means we can write p of x as a product between x minus 1 and the newfound quotient. Looking at this quotient, I want you to resist going back to a long division exercise. It's a quadratic polynomial that we learned to factor in grade 10, and you can factor using complex factoring skills. Guess and check will be the fastest. And if you take a look, it's actually factorable into 3x minus 1 and x minus 5. Always check that the outside terms plus the inside terms add up to equal the middle term of that quadratic polynomial. And this way we successfully factored p of x. A slightly more complex example in front of us, with more complex factors of the constant and the leading coefficients. You're gonna say, are we expected to look at all these various factors? We have, quite a few possibilities. It's going to take forever to evaluate all these factors in order to figure out which one generates a factor of p of x. However, I promise you that in time you'll get better at spotting factors, like I mentioned in the previous lesson. As you can see, there are quite a few factors here, and I'm urging you to take it one step at a time and start, of course, with the polynomial at 1. Let's see what the polynomial at 1 generates in terms of a factor, a remainder of 0 or not. So the polynomial at 1 equals 52 minus 44, which is different than 0. Let's try the polynomial at negative 1, because that's the next factor that we can use. As you can see, it generates a very large negative number. The polynomial at 2 equals 6 times 8 is 48, minus 32 times 4 is 128, 46 times 2 is 92, and then minus 12. And we actually notice that the polynomial at 2 equals 0. We weren't that long into discovering that x minus 2 is a factor of the polynomial p of x. As soon as we find a factor, what do? We go back to our long division knowledge, and we're going to perform the long division between p of x and that x minus 2 factor, in hopes that we're finding a quotient that could be possibly factorable even more. So let's divide p of x by x minus 2. And again, I want you to take a couple of minutes and perform that division on your own. Practice does make perfect. So 6x cubed minus 32x squared plus 46x minus 12 divided by x minus 2. Please use all your skills and check your answers. You should get a remainder of 0, right? Because we know x minus 2 is the factor. And we found a quotient based on this long division of 6x squared minus 20x plus 6. Now use your amazing skills and factor the quotient. You could common factor. You notice that every single term in that quotient is divisible by 2, and you could first common factor a 2. That might make that polynomial easier to factor if you factor a 2 out of it first, and then you're gonna be left with a slightly simpler complex trinomial, quadratic trinomial to factor. Now my result was 3x minus 1, x minus 3 in the quotient, with a greatest common factor of 2 in front of it. Thank you, and I hope you enjoyed today's lesson.